So then, if you awaken from this illusion,
persistence of vision,
ladies and gentlemen, welcome to the Persistence of Vision podcast, speaking to all the children of the earth on land, sea, or in the air, and even in outer space, inspiring conversations through talking about books. Yes. I'm host L.B. Dio.
And I'm Lance Fever Myers. Hello, folks. This is Persistence of Vision. If you didn't know, we have a website. It is pov-publishing.com. Again, pov-publishing.com. There you can read poetry, you can read essays, you can read comics by world-class sequential artists, as I like to call them. And you can see a link there to go order my book, which is called Why So Much. So go there. Again, the address is pov-publishing.com. Check it out. You can also listen to all our podcasts there. The links are stacking up. LB, who do we have today?
Well, you know, Lance Fever, years ago, I wrote a book with my partner in crime, Lefty Lebowitz, called Invisible Frontier. And we assembled a crack team of scientists and non-scientists, of which I was the latter. And of the former, we had George Brazen Raisin Musser. George Musser is an editor, a scientist, a Cornell man, and of course, the author of the recent Spooky Action at a Distance, a book about quantum mechanics and its more bizarre permutations and connotations. George, we are very excited to welcome you to the show.
Hello, George.
Hi, I'm excited to be here.
Thanks for joining us, man. I really dig this whole subject matter. It's quite arcane, but it's super fascinating. So tell us, what is spooky action at a distance?
Oh wow, where to begin? Let me just say that our assumption we make in physics, chemistry, biology, daily life generally is that we are spatial and temporal creatures, that everything that happens to us, that everything we do happens in space and time. We have a location, we reach out with our arm and we can touch things, or photons can pour into our eyes. Everything happens through space and time. And this has been just a bedrock assumption of physics going all the way back to Democritus or before, whenever physics is considered to have begun. But there have been these intimations that maybe not everything works by those rules, that maybe things are non-spatial temporal. And the kind of technical term we apply to that is non-locality. The idea is that locality is spatial, non-locality is somehow non-spatial. And there's been a variety of ways that can happen. The notion of gravity that we're taught, or should be taught in high school and earlier, Newtonian gravity is a non-local theory. The idea that the Earth reaches out and grabs the moon, that's non-local. That kind of went away. Now we have a more sophisticated understanding of gravity from Einstein, which is local. But then there's been these new ways that non-locality, non-spatiality has come into physics. And as you say, the main one is quantum mechanics. And that's where the whole spooky action at a distance comes from. It's a quantum mechanical phenomenon that we see.
So I'm sorry to interrupt, George, but it seems to me that
Do it.
You're going to drive me quite out of my mind. You're telling me that the more conventional assumptions that I have about everyday life, like the idea that if I punch my wall hard enough, I'm going to hurt my hand, that there is a distance between me and my friend and crime partner Lance Fever Myers, and that it would take time to traverse that distance at a certain velocity. You're saying that these things are not to be depended upon?
Yes, that's exactly what I'm saying. Now it's cool, right? It's almost the very definition of magic, that there could be influences that aren't mediated by space and time. You could punch and then immediately knock, give a nosebleed to your friend who's thousands of miles away. But here's the see, it has levels here, and it gets more interesting the more you delve into the subject. on the whole, our assumptions of spatiality, of locality, do hold. So nature's playing this kind of game with us here. It's almost like bait and switch. So we have these hints, tantalizing hints of non-locality, but at the space-time generally is okay. So locality generally does hold. So there's this kind of weird mix in the world of these two sets of phenomena, and that's actually really what the mystery is here, how we can have a coexistence of two seemingly incompatible ideas.
So let's back up a little bit and
Yes.
talk about. So the title comes from Einstein trying to explain or trying to describe how he felt about a particular phenomenon having to do with quantum entanglement. Is that right?
Exactly right. So you have to rewind back to the early part of the century. The idea of quantum physics, very new idea. Einstein himself really was arguably the inventor of the theory. So he had the longest of anyone to really kind of sit with its strange implications. And one is that, you may have heard, one way to come at this is that nature is both wave and particle at the same time. It has both wave and particle aspects to it. What does that mean? One is the particle aspect is that energy comes in these little packets that we call electrons, photons, etc. It comes in this particulate packaging. But on the other hand, we've got these wave phenomena. What does that mean? A wave is a spread out phenomenon. It's a spread out effect. It connects different points in space and causes them to behave in a kind of synchronized way. And the combination of those two ideas seems really almost impossible by definition. And one way to think about it is that the particles are kind of having an influence on one another or even on themselves, because actually particles can influence themselves, and that's a separate question. But certainly different particles can influence each other at a distance apart from each other. This is where the whole expression spooky action at a distance comes from. Now, what's funny about this, and I actually talk about this a bit in the book, the idea of action at a distance has been around in physics for a long time, with gravity theory and with even electrical magnetic forces. It's kind of gone in and out of fashion. Einstein then called it spooky action at a distance because this kind of action at a distance you get in quantum mechanics is very different from the earlier kinds, and in some ways more insidious and kind of harder to really understand.
Yes, you specifically mentioned a magical punch where I punch someone in a far-off place. It sounds extremely insidious.
That actually, funny you say that, because that's the non-insidious version. If you could actually punch someone who's not actually connecting to your fist, you punch someone that's far from that. In other words, you're having this distance action on them. That would actually be almost easier to understand, because you'd have this kind of straightforward, I get it. I can punch someone at a distance, or I can wave my wand and exert a force at a distance. What's happening with the spooky action at distance is kind of this weird melange, this kind of weird juxtaposition of distance effects and local effects at the same time. That's why it's spooky. That's why it has this added kind of element to it that is so weird, and it troubled Einstein so much. For instance, here's one way that it's spooky. We can have these particles that have these connections among them, between them, such that when you act on one, the other seems to be affected by that. But you can't use it to transmit a signal. You can't actually use it to punch your friend at a distance. You can't use it to exert any kind of influence. So on the one hand, nature allows this kind of violation of our spatial intuitions. On the other hand, it doesn't allow it. It's just, I don't know if I'm making any sense, but I'm trying to get across it's the combination of these two ideas that's the weird thing.
Well, if you'll indulge me just a second here, I kind of want to get to the meat of it, the heart of. Okay, so
yes, please.
You create, and correct me if I'm wrong, because I am in no way a scientist here, but the way I understand it is you create somehow you at a common origin spot of origin, you create these two particles, and they fly off at different angles, but they have a common origin. Is that right?
Mm-hmm. Yep, exactly. You got it.
And those two particles are entangled partly because they had a common origin, the way that they were created. And then one way, I guess, to do it would be polarization is the direction of the wave, or the orientation of the wave, right? So if I were to and these are two discrete particles that have their own identities, and one goes to the moon and one stays in my lab, and before I measure their polarity, it could be anything. But when I run one of them through a polarization, the one on the moon, the next time I check it, when I measure that its polarization, it's going to match. Is that right?
Exactly. Yeah, you got it. You got it completely right. So here's the case.
You sure sound like a scientist, Lance, and you even have a lab.
But why would that not say for example, I've got a team on the moon, and I say if the polarization is at a 90-degree angle, then that means everything's okay. And so I polarize mine in the lab at 90 degrees. Why would that not be an instantaneous signal to them?
Yeah. So this is where you're getting into an excellent question. You're getting to both what makes it mysterious, actually. So let's just back up and do the experiment again, and let's actually talk about polarization. So I can prepare a particle, say a photon in this case, in a superposition of both horizontal and vertical polarization. So it's like a Schrodinger cat kind of situation. Instead of having an alive and dead cat, I've got a particle in two mutually incompatible polarization states. It actually works. The whole cat thing, actually, if you want to think in terms of cat, you can. The photon is acting like that alive and a dead cat. So you've got this particle in this superposition state, and you measure the particle, it will return a random result. This is the well-known uncertainty of quantum mechanics. All good. Nothing mysterious. Well, except if you think randomness is mysterious, but nothing terribly mysterious about that. Okay, suppose you have another particle. You also prepare it in this superposition. It too, when you measure it, its polarization returns a random result. It will either be horizontally or vertically polarized, 50-50, let's say, at the time. Again, no biggie there. But the entanglement comes in because the randomness on both sides can be, it's what happens to one randomly is the same as what happens to the other randomly. This is very different from randomness that we encounter in daily life, and this is what makes it mysterious. Now, maybe I should back up and just give an elementary metaphor. The way I like to think of it is in terms of you're flipping coins. Each of those particles can be polarized in one way or the other, 50-50, is sort of like a coin. You can actually use it. In fact, you can go online and create random numbers using this kind of phenomenon. So it's like you're taking a coin, flipping it. It's either heads or tails, 50-50 at random. You take another coin, flip it. Again, it comes up randomly, heads or tails. And normally in daily life or in casinos or anytime this happens, those two events are independent. So if I flip a coin, it almost is the very definition of randomness that it's not dependent on what the other coin is doing. The two are independent of one another. But with entangled, yes, this is ordinary. This is the ordinary stuff. Now, What happened with entanglement is that you would flip the coins, and they would always come the same result. So if I flip one coin, it's heads. The other is heads. If I flip one tails, it's tails. It's always the same.
But the reason you can't send a signal is because you don't control whether it's head or tails.
Yes, you got it. So what happens is your laboratory on the moon, they tried to flip their coin. They just get a random series of results, heads, tails, whatever. Or in terms of polarization states, horizontal, vertical, horizontal, vertical, whatever. On Earth, you also get a random series, horizontal, vertical, whatever. It's only when you compare them that you would then retroactively say, what? How did this happen? How did these random results have this pattern built into them? A pattern that was only evident when I compared
so
them.
these concepts of whether the universe is one thing or many things, whether the universe is continuous or discrete, these are questions, as you say in the book, that go back to ancient Greek philosophers and ancient Chinese philosophers. But you make an interesting point about this subject in particular, this non-locality and its mysteries, where you are talking about the important contributions that are being made, or at least attempted, by philosophers as well as scientists in the modern era.
Yeah, I mean, this is a subject that really benefits from the insight that philosophers can provide. So, I mean, I think that's really whenever you go to the frontiers of science, physics, cosmology, biology, ethics, kind of ethics of biotechnology, for example, that's really where the philosophers can really help and are needed. And you see this not just in physics, you see this, as I said, in cosmology, brain science, and these other areas. So specifically in quantum physics, the worries that Einstein had raised and that Niels Bohr and the others of his time really did try to grapple with, although those two men disagreed. They basically they were common spirits in this search. A lot of those concerns got subsumed. They got kind of bracketed or shelved going into the 40s, 50s, even in the 60s and beyond. And it was really kind of a union of philosophers and of really philosophically minded physicists who resuscitated the whole subject. And really beginning in the 80s and 90s is really when this re-entered the mainstream of physics, again, due to kind of this pairing of philosophical thought and physical thought. Engineering as well. So it's kind of been a very multidisciplinary enterprise and continues to be. So I just got back a few weeks ago, actually 2 weeks ago, from a conference, a Foundational Questions Institute conference that, again, is a conference that mixes philosophers, cosmologists, physicists, neuroscientists, people of different areas, all finding common cause on these frontier questions.
There is a reputation, I believe, that physicists have, though, for finding themselves surrounded by philosophers, religious people, even people who believe in the occult, and finding these people are all very interested in participating in what they're doing, and that the physicists are at pains to point out that they are really not particularly interested in collaborating with non-physicists. Is that fair, or is that
it depends? It depends, obviously, on the person and on the types of problems that people are tackling, and not everybody can contribute to this field. So they do kind of have to cherry pick a little bit, right? But I'm talking specifically of the kinds of philosophers of physics. I mentioned some of them in the book, or even Janan Ismail is one that I just cited now, who really are really experts in the physics. They've worked with it their entire careers. So they come to the physicists prepared to contribute. They're not just kind of spouting something that they read. They actually really had thought this deeply through. And they come with a precision of thought that actually helps on this very question. Because here's the thing. Quantum mechanics is extremely well tested. There's been no deviations of the theory. All the experiments that have been done prove its results. The question that quantum mechanics raises isn't an empirical one so much as an interpretive one. So it is one that actually demands careful thought and rethought of kind of what we already know. We just have to think about it in a new way. Hence, the philosophers are good at that. Now, in other areas of science where the question is more empirical, it's like, is it 5 or is it 6? We need to go and measure in the lab whether the value of that parameter is 5 or 6. You're not going to get much help from philosophical analysis. That's just something we have to go and find out. But this is a slightly different subject. This is a question that's interpreted by its very nature.
I was gonna chime in and say as annoying as it can be when someone wants to grab onto some sort of weird behavior that we see in quantum physics and just run with it and start to come up with all kinds of religious or philosophical implications that it brings to the table. I think it's kind of inevitable. I mean, your book talks about having to reinterpret how we picture time and space and reality, really. I mean, because that's what it boils down to. So of course it's sort of inviting that sort of interpretation, that sort of I mean,
but at the same time you're saying that there, in addition to the quantum flapdoodle that might be emerging, there are actually serious contributions to be made by philosophers of science.
Yeah, I mean, a couple minutes ago I used the word holistic. And there is a word with a lot of baggage. So I was using it in a very specific sense, very specific sense that kind of the whole is more than the sum of its parts. And I can back that up with the kind of technical ideas but some people might hear the word and then bring in their own interpretation of what they mean by holistic and think of holistic medicine or whatever. And, maybe those ideas have some validity or maybe they don't, but the quantum holism has nothing to do with it. It's a separate topic. It's something that it's a kind of an interesting and probably extremely deep and will have philosophical and religious implications when it's worked through. But we need to take things in a step-by-step way and not kind of bring in some kind of presupposition about how the world should be and then see that in science and say, aha, it's confirmed my prejudice about how the world should be. So I'm working a fine line here, as are the physicists who get in this field, that it is a phenomenon that it does seem paranormal, but it isn't paranormal. This is something we can test in the lab. This is very different from other paranormal claims because this is one we can actually get at, and it's extremely limited and kind of specific and narrow, and therefore is not related to these other paranormal claims. So you don't want to be scared off an important research topic because some people might misinterpret it.
True. But you talk about magic in the book. You talk about an interesting aspect that you've touched on already, the historical presence of magic as a subject of study by scientists or proto-scientists and even as a subject of study by some of the most important and brilliant scientists who ever lived, including Isaac Newton.
Yes, I think this is absolutely a fascinating part of the story, and it's interesting. Just take a step back. So when I was working on the proposal for this book, I really wanted to focus on my initial kind of proposal and development of the project was to focus on the current research that people are doing in the labs and at the blackboard. And my agent said, I think you really need a history chapter here. So the history idea of talking about the history actually, it was something I kind of had to grow into. And it's like, well, I wasn't sure about that. But then when I started to go into this, I realized the very same issues that are being dealt with today were really articulated very early on in the history of natural philosophy, even preceding the development of what we call physics. And in those times, in the intervening millennia, there was a kind of effervescence of ideas. And some people argued that and it actually, maybe most people in this area thought that the world had these almost supernatural connections within it, and that this is where ideas of astrology back, when they were still fairly respectable concepts 1,000 years ago, or even hundreds of years ago, this is what they gained their purchase on, that maybe planets could influence events on Earth because there wasn't that really such a distance, or the distance between them wasn't that meaningful. So I think, ideas go through development, and things that we take for granted today weren't accepted a century ago, and conversely, things that a century ago people believed in, we no longer believed in. This is just the progress of intellectual thought. So it was entirely rational for Newton to do alchemy experiments, for Kepler to be interested in astrology. It made a lot of sense. And a lot of the ideas that then became science owe their origins to these ideas. And we can't we shouldn't look away from that. So forces, the Newtonian concept of a force, came from this idea that different objects in the natural world could show affinities to one another that didn't have any kind of mediation mechanically. So Newton was operating in this almost magical framework, very different from what Leibniz and Descartes thought. They thought that actually, no, there weren't these influences. Everything could be reduced to simple collisions of atoms. And Newton showed naturally, no, you can't do that. The simple collisions of atoms don't explain electrical and magnetic phenomena. They don't explain light in particular, and they certainly don't explain gravity.
But
yes,
George,
please.
I'm sorry. But do you find, as I do, that the whole concept of a force, while that actually makes sense that it comes out of this occult background, because it's a very frustrating aspect of physics, that it seems to be almost like a just a placeholder almost. I mean, I could be mistaken here, but I think the Insane Clown Posse was right that we don't, for example, understand why magnets attract or repel each other. Is that right?
Yes and no. So, I mean, again, things go through stages. Today, with our modern understanding of interactions, including the electromagnetic interaction, we don't really speak about forces in the way we used to. Force is kind of an approximate notion that works very well for kind of government work. It works for understanding the solar system and magnets and so forth. But if you were to ask what's really going on, we would actually talk in terms of fields, and that the things we ascribe conventionally to forces are actually the behavior of fields, which have no element of action at a distance to them. They're purely local. What happens to a magnet or a compass needle is the magnetic field at the location of the compass needle. There's no force transversing from one point to the other. There might be a wave going through the field that would then transmit. If I wave a magnet, the compass needle begins to kind of vibrate. That's because the field has been permuted or perturbed by the waving of the magnet. It kind of there's a wave that is set out that goes across the field and causes the compass needle to move. So we tend not to use, at least in the advanced physics, we tend not to use force concepts. And this is also true with gravity. We don't think of gravity as a force in the conventional sense anymore. It's due to the curvature of space-time. So the idea of force kind of came into physics, then it still kind of went back out of physics. We talk about forces, of course, on a routine basis, but we don't really think they're there.
That's interesting that physics kind of anticipated my objection and made a little correction to its procedure so that it wouldn't offend me.
Precisely.
I do find it really fascinating, though, this like the interplay between empirical data and interpretation and the narrative that we have to tell ourselves in order to feel like we understand. Like so you can look at all this data, and until you've actually written yourself a little story about it, it doesn't really gel. And I feel like that's a very human thing. That's a very it's a thing we all sort of need in order to feel like we have a resolution, with whatever data we're coming across. I mean, and I think that's kind of a big theme of your book, if I'm not mistaken.
Yeah, I mean, we're trying to make sense of nature, and we do that by forming, as you put, narratives about how the world is created. And that's what physics and the other natural sciences, or all sciences, do. And here's a case where we are still struggling to come up with a narrative for how those particles that are separated by vast distances can nonetheless act in a coordinated way. And there's other instances I go into of similar puzzles in physics for which we currently lack a narrative. And I think the narrative, at least my reading of the physics as done today, our best guess, in other words, that the narrative is going to involve some modification to our space notions of space and time. I think that's kind of the only way we can really get out of this this conundrum that we're in.
You make it sound so easy.
Yes, it's so simple.
It's a big undertaking.
Yeah, there's nothing easy about it, obviously.
So, George, I do have to ask one question before we go to our lightning round. Fucking magnets. How do they work?
When I don't know if you want a tweet explanation or a deeper explanation.
I think LB's got some sort of fixation with the
Well,
insane clown posse.
Listen, I'm going to be honest
a
here.
Juggalo theme running through our podcast.
Here's what drives me crazy.
Yes, talk to me.
Everyone makes fun. Listen, I'm not an insane clown posse fan, but everyone makes fun of them for saying magnets. How do they work? And my idea is, I don't think anybody knows how they work. Now, tell me if I'm wrong about that.
Well, it's one of these funny things. What does it mean to really understand something? So, yes, we do have a description of how magnets work, as I said, based on modifications to the electromagnetic field. And magnets, unlike electrical forces, have this extra element of they involve motions of charges. So we have to understand those in a relativistic way, using Einstein's special theory of relativity. So yes, we can give a perfect explanation for why magnets work. But then you might ask, were you to be LB, why that theory? Why do we have electromagnetic fields? Or why do we have photons? And why do we have the electromagnetic interaction? And then I would say, well, it seems to come out of this electroweak interaction. You would ask me, what does that come out of? And there's going to obviously come a limit to my ability to provide convincing answers to you. And the answer ultimately would be no. We don't, at a deep level, really know why magnets work or gravity works or whatever works. That's still awaiting a theory of everything. But that doesn't mean we can't get these staged
That's
ideas.
all I needed to know.
We can go stage by stage, dude.
All I needed to know.
So, am I right in characterizing our body of knowledge as a castle built on a cloud?
Einstein did actually use Luft, whatever castle was in German. Did actually use that castles built on clouds, but no, I think it's more just like any kind of construction. It's a step-by-step process. It's maybe the difference actually from ordinary buildings and castles and so forth is that we're kind of building down. So we know what we see. We just don't know what the foundation that they're built on is. But there's something there. I mean, nature works. I mean, everything in the natural world, operates. So it's really us humans' problem in a way. It's not nature's problem. Nature is just going to go on and do what it does. It's our inability to really create a convincing narrative for ourselves that's making us perplexed.
Building down.
Beautiful.
I like that.
There you go.
Well, you know what a favorite phenomenon of nature is? It's lightning. And that means it's time for our lightning round.
Aw,
Here it comes.
that's funny.
Here it comes.
Oh,
Are you ready?
I'll do my best.
Okay, here we go. All right. When was the first time you fell in love with a book?
Oh, probably I was just before my living memory. But one book, I remember, I still have it actually all these years later. Watership Down. I loved that book when I was 8 years old or whatever that was. So a lot of those early books I remember were either books about space and the solar system or were novels.
Okay. Good answer. I like it. Has a book ever changed your mind about anything?
Oh, God, that's a good question. I mean, we humans, do our minds ever change about anything? I will say I can't think of a book that's changed my mind like 180 pivot, but books have softened my certainty. They make me question my own self-confidence in what I thought I believed. So I may not have turned and pivoted, but I certainly softened my view, and maybe I'm a bit more tolerant of people who have opposing views.
Okay.
I like it.
Has a book ever changed your life?
God. Well, in a narrow way, the books on some of the early books on non-locality changed my career and made me write a book on non-locality. So certainly early when I was a kid, books on space and got me interested in space. So I don't know if they've changed my life in any other. Well, my wife actually is a Victorian literary theorist, and I read some Victorian novels before she did, and that made me feel awfully good about myself. But also, she then went on to write some of her own scholarly work on those books that I had read. So I've always felt I maybe introduced her to her career choice as well.
Sounds like she would be a good guest on the Persistence of Vision podcast.
Maybe.
Has a book ever... I'm sorry, what?
No, go ahead.
Okay. Has a book ever made you cry?
Oh,
George?
I'm a I'm that kind of person. I tend to cry and I get very emotionally invested in TV shows and
like
books.
that.
So yes, pretty much any book with any kind of emotional outcome. You hear the sniffles.
There's no crying in science, George.
Yeah.
Okay. Name a book you've read more than once.
Oh my God. I actually haven't read a book more than once in a long time, but certainly books like To Kill a Mockingbird, I probably read 10 times when I was a teenager. The Hobbit, I probably read a number of times. Lord of the Rings, I think the one time was enough. I couldn't bear to go through that whole thing again, but some of those early iconic books I certainly read more than once.
Lovely.
Name a book you've read half of.
Oh, it's funny you say that. So
Just kidding.
Daniel Kahneman's Thinking Fast and Slow is a book that I love, but I've never actually read it from top to bottom. I probably read the whole thing more than half, but I read it in piecemeal. I read chapter 1, then chapter 20. I bounce around in it, so maybe that qualifies.
What's that David Foster Wallace math book?
Everything and more.
Everything and more, right. A Brief History of Infinity or something like that. I've read that halfway about 5 times.
Next time you just need to start halfway through and then you're good.
Oh, it gets to, the first half is incredible, but it loses me, and I'm just not smart enough for that guy.
I took it back to the bookstore and I said, listen, I was told there would be no math.
Gravity's Rainbow, I think I only got about halfway through that there's another one.
Yeah.
I'm there too, and I've read the first half of that multiple times. But okay, the final question, the $1 million question for you, George, is: do you have any poetry committed to memory?
No, I don't. I'm terrible at this. I've got like song lyrics and things, but I never was a very good at memorizing poetry, and I've been kind of a black sheep in the family because of that. But I'm just not good at memorizing things, man. And maybe that's one reason.
I think in the light
I
of
think it's one reason I went into physics.
Fair enough.
Because I couldn't memorize all the
Of
proteins.
course, fair enough. You are not alone. Very few guests have actually graced us.
Oh,
with
God, I'm sorry
memorized
to let you
poetry.
down.
In the light of your scholarly achievements, we're going to allow you to recite some lyrics.
Got any AC/DC in there anywhere?
No.
A little Irving
Sorry.
Berlin.
Okay. Well, it has been wonderful to have you, George. And the book is fantastic. And anyone out there interested in the craziness of quantum physics should pick it up. It's a great read, and it really helps to explain it and explain why. Who was it? Feynman that said, "If you think you understand quantum physics, you don't understand quantum physics."
Yes. And I can't let you leave, George, without raising the alarm bell, though. There are going to be a lot of people who have listened to this interview and are going to say, well, I told you astrology and magic were real.
Yeah.
Do you have anything to say to them?
I'm an empiricist, and I don't have any preconceptions going into this. If someone could prove that they occur, I would go with it. But the empirical fact is they don't. There's been no evidence of this, and frankly, a lot of the claims just kind of don't make any sense. But keep proving it. They've got an uphill battle. Extraordinary claims, extraordinary evidence, but that's my feeling about this. I come at it from a completely empirical point of view.
You're a
like
scientist, a man of science. Thank you, George Musser, author of Spooky Action at a Distance, among many other, including I've always thought of sort of humorously titled Complete Idiot's Guide to String Theory.
Aha. Good stuff. Thank you,
George.
Very much. This has been Persistent of Vision podcast. Go to our website, please, pov-publishing.com. Buy my book, buy L.B. Dio's book that's coming out September 21st. It's called The Goddamn Fool. You can come to the release event at Malvern Books in Austin, Texas that night. Again, that's September 21st.
Yes, and go to Amazon and buy George's book. Spooky action at a distance. Thank you, George.
Thank you now.
See ya.